Imagine seeing the entire history of the universe in just one image. From the explosive birth of the cosmos to the formation of stars and galaxies, this stunning visual takes you on a journey through 13.8 billion years of cosmic evolution. The story starts with the Big Bang, a moment that created space, time, and energy. In the first few minutes, the universe was a hot, glowing soup of particles. Over time, these particles came together to form the first atoms, and eventually the first stars began to shine. As the universe expanded, galaxies formed, clustered, and collided, giving birth to new stars and even planets. Some of these planets would eventually host life, showing just how small we are in this vast cosmic tapestry. This incredible image captures everything from the birth of light in the early universe to the stunning spiral galaxies we see today. Every color, swirl, and speck tells a story of cosmic evolution, star formation, and the incredible scale of space and time. What makes this image even more fascinating is how it compresses billions of years into something we can visually grasp. Scientists and astronomers use data from telescopes and space missions to create such visual timelines, helping us understand our place in the universe. It's a reminder of how far we have come and how much more there is to explore. Every glance at this image sparks wonder, curiosity, and a deeper appreciation for the mysteries of the cosmos. If you have ever dreamed of traveling through time and space, this image is the closest thing you can experience from Earth. Share this cosmic journey and let others mark. The Big Bang Theory is the leading explanation for the origin and evolution of our universe, proposing that the universe began as an infinitely hot, dense point and expanded rapidly around 13.8 billion years ago. This theory is supported by a wealth of observational evidence from many fields of science, including cosmology, astronomy, and particle physics. The term Big Bang was coined by British astronomer Fred Hoyle in 1949, though he was actually a proponent of the rival steady-state theory. The concept of the Big Bang has its roots in the early 20th century. In 1912, American astronomer Vesto Slipher observed that most galaxies are moving away from us, suggesting the universe is expanding. This was further supported by Edwin Hubble in 1929, who formulated Hubble's law: the farther a galaxy is from us, the faster it is receding. This implied the universe is expanding uniformly. Georges Lemaitre, a Belgian priest and physicist, proposed in 1931 that the universe began from a primeval atom, an early version of the Big Bang model. Several key observations support the Big Bang theory: the cosmic microwave background radiation (CMB), the abundance of light elements, galaxy distribution and redshift, and primordial nucleosynthesis. In 1965, Arno Penzias and Robert Wilson discovered a faint glow of microwave radiation filling the universe, a remnant of the intense heat from the early universe. This CMB is a critical piece of evidence, as it matches the predictions of a hot, early universe. According to the Big Bang nucleosynthesis theory, the early universe was hot enough to fuse protons and neutrons into light elements like hydrogen, helium, and lithium. The predicted ratios of these elements match observations. Galaxies and galaxy clusters are distributed uniformly on large scales, and their light is redshifted, indicating the universe is expanding. Nebulae, the vast and breathtaking clouds of gas and dust in space, are the birthplaces of stars, planets, and even entire galaxies. The formation of a nebula is a complex process driven by the gravitational attraction of interstellar gas and dust. This material can originate from two main sources: the leftover gas from the Big Bang, which occurred about 13.8 billion years ago, or the expelled remnants of dying stars. The interstellar medium, the raw material for nebulae, is composed primarily of hydrogen and helium gases, along with traces of heavier elements and dust particles. This material is spread thinly across space, with densities so low that a typical nebula might contain only a few atoms per cubic centimeter, a far cry from the air we breathe, which contains about 10 to the power of 19 molecules per cubic centimeter. Over time, regions of this gas and dust begin to clove together under the influence of gravity, causing the material to collapse inward. The process often begins with a disturbance, such as a shockwave from a nearby supernova explosion, which compresses the gas and dust, triggering the gravitational collapse. As the cloud contracts, it starts to spin faster, much like a figure skater pulling in their arms, and flattens into a rotating disk. The center of this disk grows denser and hotter, eventually forming a protostar, the precursor to a star. Surrounding the protostar, the remaining material forms a protoplanetary disk, where planets may eventually form. Not all nebulae form from gravitational collapse, however. Some, known as supernova remnants, are created when a massive star explodes, ejecting its outer layers into space at high speeds. The Crab Nebula, for example, is the remnant of a supernova observed in 1054 AD. Other nebulae, like planetary nebulae, form when a dying star sheds its outer layers in a gentler process, creating a glowing shell of gas that is illuminated by the hot core left behind, known as a white dwarf. Over time, the gas in a nebula may clove to form stars, or it might disperse into space, depending on factors like the nebula's mass, temperature, and exposure to nearby radiation. Young, massive stars in the nebula can ionize the surrounding gas, creating glowing emission nebulae, like the famous Orion Nebula. Alternatively, if the gas is dense and cold, it can collapse to form new stars, a process that can take millions of years. Nebulae come in various types, each with distinct characteristics. Emission nebulae glow brightly, powered by the ultraviolet light from young stars. Reflection nebulae reflect starlight and appear blue, like the Pleiades. Dark nebulae such as the Horsehead Nebula, are dense clouds that block light from behind them. Planetary nebulae are the ejected outer layers of dying stars, often with intricate shapes. Supernova remnants are turbulent, expanding shells of gas from exploded stars. The study of nebulae helps astronomers understand the life cycle of stars, the origins of elements, and the evolution of galaxies. The pillars of creation in the Eagle Nebula, for instance, show how interstellar gas is sculpted by radiation from nearby stars, while the Carina Nebula reveals the chaotic birth of massive stars. Through telescopes, nebulae are not just beautiful cosmic clouds, they are the universe's way of recycling matter, breathing life into the next generation of stars.
Voyager 2, launched in 1977, has been exploring the far reaches of our solar system and beyond, sending back groundbreaking data that's reshaping our understanding of the cosmos. This spacecraft is the only human-made object to have visited Uranus and Neptune, providing the first close-up views of these ice giants. During its flyby of Uranus in 1986, Voyager 2 discovered 10 new moons, 2 new rings, and a magnetic field tilted at 55 degrees off-axis. It also revealed the planet's atmosphere is mostly hydrogen, with methane giving it a blue hue, and winds reaching up to 450 miles per hour. At Neptune, Voyager 2 found 5 moons, 4 rings, and a great dark spot, a massive storm system similar to Jupiter's Great Red Spot. The spacecraft even captured Triton, Neptune's largest moon, with geysers spewing nitrogen gas, a sign of geological activity. Now in interstellar space, Voyager 2 has detected unusual signals and energy patterns that don't match known natural phenomena. Some speculate this could be evidence of a mysterious interstellar object, an unknown cosmic event, or even advanced technology. However, NASA hasn't confirmed these claims, and scientists caution it could be a technical issue or an undetected cosmic event. Voyager 2's journey has also led to discoveries about the heliosphere, the bubble of solar wind surrounding our solar system. In 2018, it crossed the heliopause, entering interstellar space, where it encountered a wall of fire, a region with temperatures between 30,000 to 50,000 Kelvin. The spacecraft's plasma science experiment, operational for 47 years, recently shut down after 15 billion miles of service. Despite being over 46 years old, Voyager 2 continues to transmit data, offering insights into the interstellar medium. Its golden record, containing sounds and images of Earth, serves as a message to any extraterrestrial life it might encounter. The mission's discoveries highlight the vast mysteries of space and our place in it.
Spacetime is a mathematical model that merges the 3 dimensions of space, length, width, and height, with the 1 dimension of time into a single, 4-dimensional framework. Instead of treating space and time as separate entities, Einstein's theory of relativity views them as interconnected parts of a unified fabric that shapes the universe. Imagine spacetime as a vast, stretchy sheet. Every event in the universe, like a person walking, a planet orbiting, or a star exploding, occurs at a specific point in this 4-dimensional sheet. The 4 dimensions of spacetime include 3 spatial dimensions, length, width, and height, and one temporal dimension, time. These dimensions work together to create a continuum where every event is described by a set of coordinates, x, y, z, t. Einstein's theory of relativity is divided into two parts, special relativity and general relativity. Special relativity, 1905, states that the speed of light is constant for all observers, regardless of their motion. This leads to some mind-bending implications. Time and space are relative, meaning time can slow down, time dilation, and distances can shrink, length contraction, depending on how fast an object moves. For example, if you travel close to the speed of light, time would pass slower for you compared to someone on Earth. This has been tested with experiments. Clocks on fast-moving airplanes tick slightly slower than clocks on the ground. General relativity, 1915, revolutionized our understanding of gravity. Einstein proposed that gravity isn't a force pulling objects, but a curvature of spacetime caused by mass. Imagine placing a heavy bowling ball on a trampoline, it creates a dip, and a marble rolls toward it. Similarly, massive objects like planets and stars warp spacetime, and objects move along these curves. This explains why Earth orbits the Sun. It's not a pull, but the curved path in spacetime created by the Sun's mass. Here are some real-world examples. Ghost particles caught at last. After more than 50 years of searching, scientists have finally detected one of the universe's most elusive particles, neutrinos, right inside a nuclear reactor, using a detector small enough to fit in a lunchbox. The breakthrough comes from the CONUS Plus experiment at Switzerland's Liebstadt nuclear power plant, run by the Max Planck Institute for Nuclear Physics. For the first time, the team observed the rare phenomenon called coherent elastic neutrino nucleus scattering, CFNS, in a reactor environment. Here's how it works. Instead of bouncing off individual protons or neutrons, neutrinos interact with the whole atomic nucleus, causing a tiny recoil. Imagine a ping-pong ball gently nudging a parked car. Using ultra-sensitive germanium detectors just 20.7 meters from the reactor core, researchers recorded 395 plus or minus 106 neutrino interactions over 119 days, perfectly matching predictions from theory. This achievement, first predicted back in 1974, opens exciting possibilities for portable neutrino detectors that could monitor nuclear reactors' energy output and fuel status in real time. It also provides a powerful new window into physics beyond the standard model, potentially uncovering new particles or forces. With upgrades already underway, the CONUS Plus team expects even more precise measurements soon, promising to push the frontiers of neutrino science further than ever before. We humans live in a strange paradox. The majority of reality is hidden from us. Astronomers estimate that about 95% of the universe is made up of mysterious dark matter and dark energy, invisible to the naked eye and detectable only through advanced science. But the unseen isn't just out there in space, it's all around us. Our senses are tuned to a very small slice of reality, a narrow spectrum of light, a limited range of sounds. Beyond those limits exist ultraviolet rays, radio waves, infrasound, and countless other signals shaping the world in ways we rarely notice. From deep ocean animal calls to ghost-like particles streaming through our bodies, modern tools are only beginning to reveal the hidden layers of existence. It makes you wonder how much of reality is still waiting to be uncovered.